The last topic in this chapter will be on circuits that combine both a resistor and a capacitor. We call these RC circuits for obvious reasons. When we combine a resistor and a capacitor into an RC circuit, what we get is we get a circuit that exhibits time-dependent behavior. Up until now, we've pretty much looked at static conditions, meaning that either uh, we we had something where nothing was ever changing, or in the case where a current was flowing, the current was steady state. If a certain amount of current was flowing, we looked a moment later or a minute later, the same amount of current was flowing. But now, with RC circuits, we will have behaviors that are changing in time. The voltage across each element can change with time, and the current through each element can change with time. We'll pretty much consider just very simple RC circuits like the one shown here, uh, which consists of a battery, a resistor, and a capacitor hooked up in series, and we have a switch so that we can define when we start the experiment. Since things are going to evolve with time, we need a definitive starting point. When we flip the switch so that we connect the capacitor and the resistor into the circuit with the battery, a current is going to start to flow through the resistor to charge up the plates of the capacitor. The question is, will this current continue on forever? The answer is no. Eventually, the capacitor will be fully charged and will have the same voltage as the battery, as the EMF. At that point, there will be no charge difference across R, and thus no current flowing through it. As a result, all of the following things will have time-dependent behaviors. The current through R will change with time. The voltage across R will change with time. The charge on C, on the capacitor, will change, and the voltage across the capacitor will also change with time. To work with these RC circuits, there are a set of equations that describe how the current flowing and the charge on the capacitor change as a function of time. And really, all you need to do is be able to apply these equations. But I'd like to show you at least where at least some of them come from. This, of course, will not be something you'll be tested on, but it's good to understand where these come from, at least to some degree. So to understand the behavior of an RC circuit, what we can do is we can perform Kirchhoff's loop analysis on this simple circuit. So if we go around this one and only loop, then the sum of the voltage gains and drops has to equal to 0 by the time we go all the way around, which in this case would include the voltage gained through the the voltage gained through the EMF, voltage difference across the resistor, and a voltage difference across the capacitor. So going in a clockwise fashion and presuming that the current runs also in that same direction, we get a positive EMF minus a voltage drop across the resistor minus a voltage drop across the capacitor, which, if you remember from when we studied capacitors, we have the equation charge is equal to voltage difference across the capacitor times capacitance. So we can write that delta VC as Q over C. Now, once the capacitor is fully charged, the current will be 0 because at that point there will be as much voltage across the capacitor as there is across the driving EMF, and no current will flow. When the current is 0, this equation simplifies to EMF is equal to Q over C, or Q is equal to the EMF, or the voltage due to the EMF, times C, which is exactly what we expect because that's the equation for a charge on a capacitor. So this is just kind of a double check that our equation makes sense within reasonable limits. Now to find the charge on the capacitor at some arbitrary time, not waiting for an infinite amount of time or nearly infinite amount of time so that we're sure that the capacitor is fully charged. If we want to look at some arbitrary time t after the switch is closed, then what we can do is we can rewrite the equation above as EMF is equal to, bringing all this stuff over to the other side, we get delta Q over delta T, which is the definition of I. Remember that I is just the change in current over the change in time. So that we'll rewrite that I as delta Q delta T times R plus Q over C. Now this is a differential equation in Q. We have something that has Q and dq dt effectively. The solution to this, again, this goes beyond the math that we were required to have in this course, so we'll just state without proof that the solution to this differential equation is q of t is equal to c times EMF times 1 minus e to the power of this whole thing up here, which is minus t over RC. Now, whereas we won't go to proving that this comes out of this, we can actually show that this is definitely a solution to this. If you go through and you plug in this for q and plug in this for dq dt, where you take the derivative of this with respect to t. For those of you who remember, when you take the derivative of an exponential, you bring the exponent down. Then you can prove to yourself that this is in fact a solution to that. Or you can take my word for it. This equation is the equation you're most interested in. This tells us the charge as a function of time depends in this form on how long you wait compared to what is called the RC time constant of the circuit. So this product RC has in fact the units of time. You can go and look up the units for ohms in terms of very basic units like meters and seconds and kilograms, and the unit for capacitance, and prove to yourself that when you take those two units and multiply them together, a lot of stuff cancels and you're left with just the units of seconds. So for example, if we hooked up a 6 kilo ohm resistor with a 7 microfarad capacitor, then the RC time constant would be 6,000 ohms times 7 times 10 to the minus 6 farads, which would give us 4.2 times 10 to the minus 2 seconds, or 42 milliseconds. So this circuit will have an RC time of 42 milliseconds. Now that does not mean that the capacitor becomes fully charged after just 42 milliseconds. So to understand this, let's take a look at what the mathematics of exponential behavior. For those of you who are comfortable using exponents and or exponentials and logs and natural logs, you can skip ahead a few minutes to the next slide. So the quick review of exponential math. This shows up in a lot of places. There's exponential growth and decay in a lot of population dynamics, including things like bacterial growth. And there's exponential decay in things like radioisotopes and carbon dating, which we will actually study a little bit in 1C. But for now, let's just look at the math. The number E is called Euler's number. It is equal to 2.71828, rounded to sig figs here. It's a fundamental number like pi, and it's just a constant that shows up a lot in nature. E to the 0th power, like any number to the 0th power, is just 1. The general formula for exponents is that if you take any number and raise it to the minus x power, that's the same as taking 1 over that number to the positive x power. So in this case, e to the minus x is equal to 1 over e to the plus x. If you take e to the minus infinity, you get 0, because you're effectively taking 1 over e to the positive infinity, and a positive number taken to the infinity power is effectively infinity. Right? 1 over infinity gives you 0. The other important thing to know when working with these exponents is that the inverse function of an exponential is the natural logarithm. Now, be sure you know the difference between natural log, which is abbreviated ln, and another logarithm often written as log, spelled out log. This refers to log base 10, sometimes written with their subscript 10. Both of these functions exist on your calculator. The inverse of e to the x is a natural logarithm. The log base 10 is the inverse function of 10 to the something power. So for this function, you have to be sure to use the natural logarithm as the inverse. So if we're going to solve an equation like, let's say you have an equation written out that says something like 13.9 is equal to 4.4 times e to the x, and we want to know what x is. Well, then what you do is you isolate the e to the x term, right? 13.9 divided by 4.4 is equal to e to the x, which gives us 3.159 is equal to e to the x. And then what we want to do is to get the x by itself, we want to take the natural logarithm of this, but that means we have to take the natural logarithm of both sides. So the natural log of 3.159 is equal to the natural log of e to the x, which is just x. So that tells us that x is the natural log of 3.159, which works out to be 1.15 when you plug it into your calculator. So let's go ahead and calculate and plot some of the values that you would get for charging a capacitor. After the switch is closed, we want to look to see how much charge is on the capacitor as a function of time. That's what this equation gives us. So if we look at this formula, we notice that the prefactor up front is the capacitance times the voltage supplied by the EMF, right? That is going to be the maximum charge that can be put onto this capacitor, right? Because after a long time, when charge is finished running, we expect that the voltage across the capacitor will be equal to the voltage across the EMF. So using Q equal VC, the total charge would be V of EMF times C. So this is the maximum charge that we'll have at some infinite time. And of course, when we first start, the instant that we close the switch at t equals 0, there is 0 charge on this capacitor, right? Because it started off empty and we've just barely closed the switch. But at a time RC later, right? And again, remember RC, when you multiply the terms together, gives you a number in seconds. So that means when we are at exactly 1 RC, let's say that this was let's see, in our previous example, we had 42 milliseconds. So let's say that we wait 42 milliseconds, right? When RC is 42 milliseconds and T is exactly 42 milliseconds, then we have e to the minus 1. E to the minus 1 turns out to be about 0.37, which means that 1 minus e to the minus 1 gives us a number about 0.63. So at t equal to 1 RC, again, in this case, we're looking at when t is 42 milliseconds, then we have the charge on the capacitor is equal to 0.632. And remember that C times EMF is the maximum charge when we wait a very, very long time. So that says that after the 1 RC time constant, 42 milliseconds in this case, we will have achieved about 63% charging of our capacitor. If we wait another 42 milliseconds so that we're at 2 RCs, then at 2 time constants, we will have moved up to about 86% of full charge, and then 95%. And eventually, when we get to an infinitely long time away, we will be approximately fully charged. But it really is an asymptotic approach to that full charge. And you can understand this because as you put more and more charge onto this plate, the back pressure on due to the crowding of like charges on this plate reduces the flow. Right? As this EMF or as this voltage across this capacitor gets closer to being equal to the EMF, there's very little difference in voltage across the resistor, so there's very little current. So charges are moving much more slowly, and the amount of charge that builds up begins to slow down, right? And you only really reach absolute full charge in the limit of infinite time. Now, if we were interested in the current as a function of time, right? We were here looking at the amount of charge stored on the capacitor as a function of time. What if we want to know what the current through the resistor is as a function of time? Well, in that case, since current is just the change in charge over the change in time, we would take the limit of this to be a derivative of charge versus time. For those of you who are comfortable with taking derivatives and remember something about the derivative of exponentials, we can break this into two terms, right? Distribute this out so that we have C times EMF by itself, but that's just a constant, so the derivative of the constant is 0. And then the second term would be capacitance times EMF times e to the minus t over RC. The exponent, the only t is in the exponent here, and so the derivative of this brings the exponent down while leaving the exponential intact, which gives us C EMF 1 over RC times the original exponential. That means the C cancels that C, and we're left with a r on the bottom, so that we get epsilon over r times the original exponential function. So in summary, when we're charging a capacitor, in other words, if we had a system hooked up here where we flip the switch over to this side so that the only complete circuit is here on this left side, and we're charging up this capacitor that's presumably empty to start with, then the charge as a function of time is given by this equation, and it has this behavior where it starts very quickly to build up charge, and then over time the amount of charge uh, approaches this maximum charge of c times epsilon, but it approaches it in kind of a slow asymptotic behavior. On the other hand, if we want to look at the current running through the resistor while it's charging, we get a different equation that's given by EMF over R times just a simple exponential, e to the minus t over RC. And that's actually shown in this bottom graph, even though it's associated with this part. All simple exponentials have this decaying behavior. So that's what you get when the capacitor is charging. Once the capacitor is fully charged, if we then flip the switch over to this side, so the battery is now out of the circuit, and we have the capacitor discharging through, let's say, a different resistor here, and then the behavior we get is a simple exponential for both the charge and the current. Right? So now both the charge and the current have this simple exponential behavior. Charge starts with an initial charge, big Q, right, and then decays down to 0.37 Q after one time constant, and then down to about 0.15 by the second time constant. The current actually has the same behavior. The current is reversed. The current is reversed compared to this situation where when we were charging, we were adding charge to the top plate. Now we're removing charge from that top plate. So that accounts for the minus sign. And then the behavior here is, again, a simple exponential. It's an exponential decay. So the current starts off very strong with a maximum current of Q over RC, and then slowly decays to zero. And this makes sense because if you think about this, we no longer have a battery, a driving force. The only driving force is the pileup of charges on the plates of the capacitor, which, remember, we got a bunch of positive charges up here, we got a bunch of negative charges down here, and then we connect it up so that the two plates are now connected through just this resistor. So by electrostatic repulsion and attraction, the positive charges are going to want to run through this resistor and cancel themselves out with the negative charges on the bottom plate. And at first, there's a lot of positive charges here. There's a lot of mutual repulsion, and that will push these positive charges very strongly through the resistor to the negative plate. Right? So the current will start off very strong, and the charge, of course, we start off fully charged. As the charge runs through this resistor and cancels out with the excess negative charge on the bottom plate, the voltage difference across here starts to drop, which means that the pressure and the mutual repulsion between charges is less because there's fewer excess charges on these plates. So the drive of the current begins to reduce. The current starts to go down, which of course means that the amount of charge that you have doesn't drop as quickly anymore. And eventually, when you have just a few excess charges up here and a few excess negative charges down here, you have very little charge, but you also have very little push to get them to go through the resistor, and so the current is very, very low, and the change in the charge, which is by definition the current, is tapered off to a very small amount. Right? So this exponential increase and exponential decrease describe the behaviors of both the charge and the current. When you're charging the capacitor with a battery through a resistor, or just simply discharging the capacitor through a resistor. And finally, just a word for those of you interested on why we study RC circuits. It turns out that there are a lot of natural phenomena that can be modeled by these RC behaviors. One important one is the RC circuit model of a neuronal membrane. Right? You can think of the membrane as a capacitor because it's a lipid bilayer that doesn't normally allow much charge to flow through it, so positive charges on one side, negative charges on the other in the form of ions. But there are also pores and channels that are slightly leaky, which allow some charge to sneak through, and hence kind of you put a parallel leak resistance through here. The inverse of a resistance is a conductance, and that's what's normally talked about is a conductance through the membrane. Um, and there are pumps that act as voltage sources, right, that pump ions from one to the other that produce this voltage difference. But the bulk of the membrane itself uh, acts as a capacitor in the sense that the charges are not allowed to easily cross from one side to the other. And as you can see, when we do measurements on the uh, voltage and current behaviors of membranes, you can begin to see these exponential rises in the membrane potential and these exponential decreases. And then these spikes here are because of active components that lead to action potentials. But you actually can see here, even in these, there are, if you zoom in on them, you would see RC-like behavior on both the upslope and the downslope.